Welcome Algebra 2. This is 11-4, Conditional Probability. The essential question is, explain how to use explain how to use a contingency table to find conditional probabilities. Let's begin. So what is a conditional probability? It's when two events are dependent. So the way to write a conditional probability looks like this. Probability of event A given event B. So you have this line right here, so we read that as a given. So probability of event A given event B. So for the probability, the way I'd say this probability here is the probability it'll rain on a person given that they are in Palmdale. And then there's also the idea of the probability it'll rain on a person. So these are different probabilities. One is it's rain on the person, it doesn't say where they're at, but if they're in Palmdale, that's a certain area, and there's a certain chance that it'll rain there, and that's different from like the rest of the world. So the conditional probabilities, you're putting a condition on that probability. So let's look at some examples of that. And as we do that, let's talk about a contingency table. So it's a frequency table where we have data from two different categories, and we can use it to help find conditional probability. So what I have here is a table on males and females and genders at colleges. So 2-year college, 4-year, and graduate schools. So the table shows students by gender and type in 2005. You pick a student at random. What is the probability that that person is female given they went to graduate school? So the given area is the graduate schools. So for problem A, I'm going to be using this column. I'm only going to be looking at this information. And I want to know how many of those are female. So the probability in this case is that probability is going to equal the number of females there are, which is 1,954, divided by the number of students in graduate school. So you kind of, some way you kind of look at it like a fraction sign. So you treat it as the probability of female over number in grad school. But you're not looking at females total, just the ones that are in grad school. So it'll be 1,954 over 1349 plus 1,954. And if you add those two up, what you'll get is 3,303. And if you reduce that, if possible, try to do that, you're going to get approximately as a decimal. Well, you can just leave it like this. And then I'm just going to leave it like that. Or a decimal would be 0.59. Now, what is the probability someone is female? Now, this is different because we're looking at the whole table here. So our females are going to be the number of females in all three columns. So 2,462 plus 5,517 plus 1,954 over everyone. So how many people are in there? And again, I can add this up with a calculator. 24 plus 1349, 2462 plus 5517 plus 1954. And I'm going to get, if I type this in right, 17,472. So that top number, if we try to figure that one out, that's going to be 2,462 plus 5,517 plus 1954. Divide that by 17,472, and you're going to get a fraction. It's 9,933 over 17,472, which reduces to 473 over 832. So that's your answer. All right, let's try a different example like that. So we have another table here. We have our material and types of material, and if it's recycled or not recycled. Americans recycle increasing amounts through municipal water waste collection. Table shows data from that. 2007. What is the probability that a sample of recycled waste is paper? So the probability that a sample of recycled waste is paper. So it's paper. So you got to be careful. Is this recycled given that it's paper, or is it paper given that it's recycled? And if you're reading this carefully, what's the probability that a sample of recycled waste is paper? So I am taking something that is recycled waste, and I'm trying to figure out if it's paper. So what I want to read this, what's the probability that's paper given that it is recycled? So you have to read those very carefully. I'm trying to figure out if something's paper out of all the things that are recycled. So I'm looking at that data right there. That's my recycled column. So how many of those are paper? 45.2 tons, millions of tons. And how many of the recycled? Well, you add all those up. And if I add all those numbers up, You get 45.2 plus 7.2 plus 3.2 plus 2.1 is 21.7. And that's going to all add up to 79.4 million tons. And so if I want to simplify that fraction, I can rewrite that as 452 divided by 794, and that'll come out to about 226 over 397. And that's your answer. All right, let's try something else. Conditional probability formula. So there's an actual formula for this. For any two events, A and B, so your probability of B given A is going to be probability of A and B divided by A. Now another way to write that, sometimes we want to use the conditional probability to figure out probability of two events happening A and B. So multiplying by probability A on both sides to get probability of A and B equals probability of B given A times the probability of A. So we might use that formula. So let's look at additional examples. A utility company asks 50 of its customers whether to pay their bills online or by mail. What is the probability a customer pays the bills online given that the customer is male? So that given helps you out there. So you want to find the probability that they pay online given male. So I can use my table here, or I can use my new formula. So that's going to be the probability of A and B, so online and male, over the probability of male. So I'm going to use my formula here. So probability of someone being online and male is 12. So we're gonna look at those fractions. So that's going to be 12 over, well, how many things do I have total? I have 20 in this column, and I have 30 in this column, so it's 50 total. So it'll be 12 over 50. That's probability of online and male. And then probability of males, well, you have your total males is 20 divided by the total is 50, so 20 over 50, which is going to reduce if you do this. Since they're both divided by 50, that doesn't matter, and you're left with 12 over 20, which reduces to 3/5. So 3/5 would be your probability of online giving male. And you know what, that'll also work out if we just look at the contingency table, because that's going to be 12 over, since we're online given their male, 12 over 20 anyways, because there's 12 males and there's 12 online and there's 20 males total, so it'll be 12 over 20, which would be 3/5. So either way of doing that, the formula or the contingency table would work out. Let's look at another example. So I'll use the formula again. Research asked shampoo users apply directly to the head or indirectly. Was the probability that a respondent applies shampoo directly to the head given, so directly to the head given female. So probability of direct given female. And using that same formula, your total number of respondents is going to be 50 again. It's 20 men and 30 females. So probability of both A and B happening, direct and female, is going to be this probability of direct and female over the probability of female, which is going to be the probability of direct and female is going to be 6 over your total 50, divided by probability of females is going to be 30 over 50. So simplifying those, again, those 50s, since both fractions have 50, the 50s cancel out. So you're left with 6 over 30, which reduces to 1/5. And that's your answer. All right, next one. So sometimes we use a tree diagram to state conditional probabilities. So what you have going on here, so this is what your tree diagram will look like. A school system compiled the following information for a survey sent to people who were juniors 10 years earlier. So 85% of students graduated from high school. Of the students who graduated from high school, 90% are happy with their jobs, so 10% are unhappy. Of students who did not graduate from high school, 60% are happy with the present jobs, so 40% are not happy. This is a tree diagram. So the first branch represents those that graduated, so 85% versus not graduated, 15%. The second branch is our conditional probabilities. Are they happy or not happy? So 90% of those that graduated were happy, so 10 were not happy. And 60% of that did not graduate were happy, so 40% were not happy. So those represent conditional probabilities here. We can use a tree diagram to solve some questions. What's the probability of a person from the junior class graduated from high school and is happy with his or her present job? So out of the total here, So you want to find out the probability that someone is happy and graduated from the total. I know those conditionals, I know certain types of people are happy or not happy, but I want to know from the grand total how many of those graduate and is happy with his or her present job. So how many from the total met both those criteria? Well, probability of grad and happy is going to be following that formula right there. So you're going to follow the probability of happy given that you graduated times the probability that you graduated. So happy given graduated is going to be right here, and that's going to be 90%, or 0.9. Times the probability you graduated is going to be 0.85%. You multiply those together, and you're going to get 0.765. So 765 thousandths. That is your probability, or 76.5%. That's it.